This dimensionality reduction, so these lectures I have taken from the book of Icham Alpaidin, Introduction to Machine Learning, and I personally feel that it is one of the easiest to understand and beautifully explained book for beginners in machine learning. And also you can go and purchase the hard copy. It has the special low cost edition for Indian market, like which is low cost, like it is 400 I guess now. So it used to be 300 something earlier. But I found the book is like, if you can have the one handbook, so for me that book suits better. So, and all the slides are there, and even the PDF of the book is also available somewhere in the net. So I will give the link if possible. So why do we need to reduce dimensionality? Say first is that technically, if you go for like a full-blown machine learning model, or in this deep learning model, so typically you will see that we have dimensions of 100 to 300 feature vectors, right? Or even thousands. So now, as many features we considered, it is going to add, multiply actually in terms of the space and time complexity. Time complexity, because as if my vector length increases or dimension increases, I need to do more number of computations. And space complexity is that I have more parameters, more features to actually tune to. So I need more storage, more space, more memory. And also dimensionality reduction saves the cost of observing the feature. You must have heard this term like I plotted the feature vector in a two-dimensional plane. So because as human, we can only visualize till 3 dimensions. So for lots of data, like in clustering, it was important for us to see actually the data instances on the 2D plot to understand how we are doing clustering. But that does mean that the data instances had only two features. No, right? So somehow, for our sake of understanding and our sake of observations, we were able to plot, say, a 300 dimension vector to a two-dimensional plane. Now, how do we do that? Can we, is there a mathematical way to ensure that while I am compacting so much, I don't lose significant information? Fourth is that simpler models are more robust on small data set. See, if your data set size is small and if you have large feature set, then your model may not actually reach this stability point. Fifth is that if we can visualize it, it becomes more interpretable and we can come up with simpler explanation. And last but not the least, we can visualize the structures, groups, and outlier, etc. So now, how do we do dimensionality reduction? So there are two main methods. One is the feature selection and feature extraction. So feature selection, I think you have covered in the decision tree. There was a lecture like how do we identify the important features based on the, the
Yes.
information gain. Yes. Yes, right. So this was feature selection, so where we chose K, where K is less than D, the whole dimension of features. From that we are choosing K features, which is typically significantly lesser than D, and we are ignoring the other D minus K features. So this is subset selection algorithms are one example of that. That how given a pre-existing feature set, how we can identify some important features. Second is that feature extraction, which we will do in the dimensionality reduction. So in this case, we are not choosing a subset of feature, but instead we are projecting the original features in the D dimension to a new K dimension, where K is significantly less than D. And in this K dimension, say if my original vector is xi, from xi, I am transforming to vectors to zj. I am reducing xi to zj in a K dimensional plane. And how will I do that is the dimensionality reduction. Okay. So in this case, I am choosing a subset of features, and in this case, I am mapping the feature onto a lower dimensional plane. So some examples are the principal component analysis, linear discriminant analysis, and the factor analysis. So in subset selection algorithm, how typically we go? Say for D features, there can be possibly 2 to the power D subsets, like the power set of a set. Say for example, if I have 3 features, so then there are 8 possible combinations for all features. So the forward search is that we add base feature at each step. So say for example, the set of feature which begin with the null set, and at each iteration we find the base new feature based on some the error function. Just a moment. Hello. Okay. And at each iteration we find a base new feature based on some the error function or the loss function of our model. So we see that if adding this new feature to my already existing feature set, if it gives me the minimum on the error function, or it minimizes my error. Okay. So typically in adding the next feature, it will be less than what was the error on my existing feature set. So there is a problem of hill climbing. So in hill climbing, what happens? Say when you are climbing a mountain is having multiple like peaks and tows, right? So when you reach a peak, so you never know that whether this is the local peak or the global peak. So you never know that whether you have actually reached to Mount Everest or you are just beginning on the smallest peak on the Himalaya. Because from a peak, wherever you go in which direction, actually your optimization will be less. So that we call like reaching a only the local maxima, which is the problem in the hill climbing, and that's why it is a like of the order of d square the algorithm, because we need to find all the d cross g combinations. Then there is another way to do a backward search, that is I start with all features and remove one at a time based on again some condition that my error function should not increase more than an arbitrarily chosen number. Say I say that I will remove the one feature. If by removing that feature the error does not increase by more than 0.0001. Okay, points. So, and way is to do, and between these two, there is another way that is called the floating search, where I add one feature or one subset of features and I remove another subset of features. But as you can see in the subset selection, the algorithm, the complexity is very high, and also there are chances that we always will not come up at the optimal feature combination, and there is a chance of loss of the information, because a feature or a well crafted feature represents an important information for a particular data set. Now, if we just remove that, no matter how my training the error is minimized, we may lose significant information that may be important down the line. So, instead of all this, what we do is the dimensionality reduction. So, instead of omitting on the features, we map all the features to a different plane or a different sets of dimensions to, and while keeping my information as intact as possible. So one such example is called, one such method, it's called the principal component analysis or PCA. As the name suggests, that we try to extract along which two or three dimensions or a lesser number of dimensions than the original feature dimension. If I plot my data, still the property of my data will be visible. And a PCA is a very frequently used methodology for dimensionality reduction. So you will find it often that after we train a machine learning model, we plot the data points using this method on a two-dimensional or a three-dimensional plane for our visualization. So, okay, I think you have also plotted in your lab classes on a 2D plane, if I am not mistaken, using something like matplotlib or other Python functions.
Yes.
Yes, no? Yes, yes. So we will see how do we, what is the intuition behind doing PCA in the next class. And PCA is again directly linked with our eigenvector and the eigenvalue discussions that we did in the earlier class. Okay. So, any question till this point?